21. I'm one of your hosts, Jonathan Ullman, alongside the anomaly of the Marshmallow Test, Tom Kea, and Mr. Malencam himself, Tyler Cohen. Tyler,
thanks for having me.
Yeah, welcome. You're our first guest to trèSci Weekly. Yeah.
Woo. I'm honored. Thank you.
Thanks so much for being here, man. So, this is going to be a little bit different format of the show that you guys are probably used to seeing. How we're going to go about it is we're going to basically allow Tyler to kind of give his own elevator pitch of who he is and what where he's come from, where his start from the bottom and now his being here, if you will. Then we will get into the show proper. We'll do the news stories that you guys come to see here for trèSci Weekly. Then Tyler is going to jump outside where he's got his telescope and the infamous Malencam set up, where we're going to hopefully be able to cut to that during the stream, during the end of the stream, to take a look at M8?
M81.
Which is
Bode's Nebula. Which is not a nebula, it's a galaxy.
So we might be able to check out a galaxy at the end.
So we might be able to check out a galaxy tonight. And while Tyler is setting all of that up, Tom and I will be here doing typical Tom's Corner for you guys, so that we basically cover all the things that we cover in a normal show and then some.
Sounds good.
Sounds good?
Sounds good to me.
All right. Tyler.
No, real quick, before we do that, like the normal spiel.
You're right. The normal spiel. Thanks, Tom.
You're welcome.
You're right. My head is a blur here. The normal spiel. Welcome to trèSci Weekly, guys. If you're just joining us for the first time, thank you so much for being here. Remember, you guys are part of the show if you're watching live. Feel free to chat with us in our YouTube live chat. We're here to answer questions and just kind of talk back and forth with you guys. If you guys have questions for Tyler, of course, feel free to queue them up in the chat as well.
Hi, Mom.
If you would like to support this show, you can do so by subscribing to us on YouTube. You can go to our Facebook page at facebook.com/trèSci Weekly and liking us there. You can go to twitter.com/trèSci Weekly and following us there to keep along with some of the stories that we're monitoring throughout the week that we like to report on. Of course, we like to hear your feedback. So if you tag us in anything on social media that you've read about in terms of science news or research news that you've heard about, we would love to share those stories with you guys. And, of course, we always throw you guys credit where credit's due. If you guys pick up on something that we didn't catch, we throw you a little credit, throw you a little bone there.
Oh, yeah.
And finally, you can go to patreon.com/trèSci Weekly if you would like to support this show financially, which of course you don't have to do because this show will always come for free. How'd I do? Was that good?
That's great.
Nailed the spiel?
Yeah.
All right. Tyler, talk to me, man. Who are you?
Well, I graduated last spring from Stony Brook University, your alma mater, and we met, I don't know if you remember, I was visiting the school, and you were a senior at that point, and my dad was like, go talk to people, and I think you were the first person that I talked to, and you started the Stony Brook Astronomy Club.
The current one.
The current one.
The current chapter,
right.
if you will.
Which I then went on to become an e-board member and later president, and the club is going strong after 7 years maybe of the new and improved club.
Yeah, right on.
But and after leaving Stony Brook, I went for 4 months to work in Hawaii on the Big Island on Mauna Kea at the Gemini telescope, which is an 8-meter telescope there.
Not bad.
That's cool. Unbelievable. That was pretty sweet. So I did a 4-month internship there, studying galaxy evolution. And now I am looking to go to grad school. I'll be starting in August. I'll be going to New Mexico Tech, which is where the VLA is. If anybody has seen Contact, that's when Jodie Foster is sitting out with the little radio, and she's sitting out, and there's like the radio dishes in the background, and the truck is out there, and there's actually no canyon by there, and there's a canyon in that scene. I mean, that bothers me every time. They just added that in. I don't even know why.
Tom's got a lot of problems with the movie Contact.
Yeah,
we can get into that another time, but
yeah, so I'll be heading out there in August to hopefully start research on gravitational waves and pulsar timing.
fantastic.
Cool.
Excellent. So you graduated Stony Brook, right? Is it all roses and peaches? Is it people are fighting to get you into their programs, or is it harder than that?
Oh, it's definitely harder. Well, I didn't get in. I applied to grad school actually the fall of my senior year, which I graduated in 2016, and I didn't get into any schools. And so it was kind of like an existential crisis for a little while,
Yeah.
but it happens. And so I reapplied, but I actually, because of that, had the opportunity to go and do this internship in Hawaii, and I am so glad that I took a year off from school because I felt pretty burnt out after Stony Brook. It's a tough program, physics and astronomy program there, so I mean, ultimately it worked out for the better, and now I'm in grad school, and I would just say keep applying. If you don't get in, don't give up on your dream if you want to do astrophysics or whatever it is, because just
gotta make it
perseverance.
Yeah,
And,
right. I didn't mean to throw you under the bus with that question. I was mainly pointing that out because I didn't apply to grad school because I wasn't really an A student,
and not everybody does either.
And your your intellect and your knowledge on the topics that you've enlightened me to are far more reaching than what I understand about these topics. And so I'm genuinely curious, like, for somebody who graduates from Stony Brook and truly knows a lot more than I did when I graduated Stony Brook, like, what is the outset? Is it people are really excited to get you in on their projects, or, as you're indicating to me, you have to still fight for it a little bit?
Yeah, you definitely. I mean, I applied to a lot of internships last summer, and ultimately I got the Hawaii thing, I think, in part because of the Stony Brook Astronomy Club and the work that I did there, because I talked about that with my advisor, before I was hired. So it was just a combination of the work that I did at school and the contributions from the astronomy club, and I didn't have people knocking on my door, but when people see, I mean, Stony Brook is a reputable school and they have a very strong physics and astronomy program, so when people see that and they see involvement in outreach through the astronomy club and things like trèSci, and that's an element that they want to add. People who can communicate science well is a very marketable talent, and it's not as prevalent as it could or should be. Yeah,
I agree.
Right on.
It stinks. I feel like it should be like the NBA draft almost. Like,
that's what I'm saying.
Who's the top physics pick? Are you a 6th rounder? Like, in the future, that's the way I want it to be.
Yeah.
Well, not exactly like that, obviously, but I would like it to be more where they're kind of looking at the prospects and encouraging people to come to them more.
Yeah.
As opposed to just you having to fight for it again after you graduate.
Yeah, because it's a daunting task, to especially coming out of college when you typically are broke in a sense, and then they charge you an application fee. It's like, wow, well, this is really, cross my fingers here.
And I wish more programs and institutions valued outreach. I was pretty pleased with Gemini Observatory because they were the only telescope on Mauna Kea that had an actual dedicated outreach department, and they did some incredible things.
Awesome.
From science shows and stuff, so that was pretty special to work at a place that does that. And I think we value outreach more. We kind of open the pool of people that can be advocates for science, and I mean, what you guys do is great here.
Cool.
Doing outreach, so
yeah.
That's why we're glad to have you on.
Yeah, we're honored to have you on the show because that's a big step for us as far as legitimizing what our mission here on trèSci is to get people like yourselves in on the fold and talk to people about
what
cool
the science is being done.
The cool stuff that everybody, that people that are in the field know about, because the universe is interesting. So,
as James says in the chat, we're recruiting soldiers to fight the war on science.
Exactly right. So, audio's a little poppy.
Because we have 2 streams up.
Okay. Yeah. Can we have you shoot outside, pause your stream?
Sure, absolutely.
And then we'll resume once we're going back. Cool.
So minor break here. No worries.
This is just this is how it goes. This is a learning process for all of us. So Tom, talk to me, baby. How's your week?
Good. I had some things I wanted to mention, like some honorable mentions. Yeah. So I've been reading a whole bunch of SpaceX news. They've been in the news a lot. They've been launching different satellites into orbit, and one of the things that they prided themselves in is they had the most re-entry force ever, I believe, re-entering the atmosphere, and that was the rocket they managed to land again as well. So and one of the tweets was like, Elon Musk tweeted like, you gotta fail where you want to succeed in this industry, and he shows all the videos where it exploded trying to re-land, and now with the largest re-entry force being able to successfully bring up those satellites and land the rocket back down, they were kind of like bragging on Twitter, like, because people doubted them and kind of talk smack, like, you guys aren't gonna be able to do this, SpaceX.
Yeah.
And here they are.
Here they are, man.
Yeah. So it's great. I love seeing them in the news.
Yeah. Right on. Very, very cool. All right. So without further ado, right? I think we should get into the news stories proper. That way we have enough time to do some night sky observing.
Yeah,
at the end of the show. So 4 stories on the docket today, guys. They're all space related because I figured we have Tyler with us, who that's his expertise is space topics.
Who doesn't like space, right?
And who doesn't like space? I mean, I love space. So here we go. Number 1. On Tuesday, June 20th, the European Space Agency's Science Program Committee announced its plans to continue moving forward with its LISA, and LISA stands for Laser Interferometer Space Antenna mission. The mission seeks to further our understanding of gravitational waves, the extremely small perturbations in the fabric of space-time that are caused by massive catastrophic events, such as the merging of 2 black holes. LIGO, or the Laser Interferometer Gravitational Wave Observatory that's located here in the United States, confirmed the existence of gravitational waves back in 2015 and has since detected 2 more confirmed stellar black hole mergers in star clusters within the Milky Way galaxy. LISA will be a bit different, being a spaceborne experiment with the sensitivity to detect low-frequency gravitational waves theorized to be associated with supermassive black hole mergers that result from galactic collisions. The fundamental science and technology needed to perform these careful measurements has already been demonstrated via ESA's LISA Pathfinder mission, which launched on December 3rd, 2015, and is set to conclude on June 30th, 2017, so just a few days from now. The proposed LISA mission will consist of, quote, 3 craft separated by 2.5 million kilometers in a triangle formation that will follow Earth in its orbit around the Sun, end quote. And we have a couple images, actually an image and a GIF video that we can bring up to show you guys what we're talking about there.
Cool.
So, the LISA concept image is the one that I'm referring to.
So we're moving from the ground to orbit.
So we're moving out into space, right? So we have ground-based laser interferometers set to detect gravitational waves here on Earth. One in Washington State, one in Louisiana. And this will now be a new experiment that takes that same sort of idea, puts it in orbit around the Sun in sort of a lagging orbit behind the Earth, which we can also bring up a small GIF of Kyle's boogieing back over to his seat there. That's going to be the LISA motion GIF. And so we can see here.
So the blue dot is Earth, obviously, right?
Blue dot's
and then
Earth.
The triangle is
triangle formation of the basically the mass and the two arms that the laser interferometry is sort of where the beam is splitting, in a sense. So we have that.
So we have talked about gravitational waves before on trèSci, just sort of saying that we've detected them as reporting it as news.
Right.
But now I'd like to throw it in your court. Now this looks like it's sort of like a step up, I guess you could say. Is this like an improvement? Because I've seen a few stories out there saying that the way we're detecting gravitational waves on the ground isn't really like the ideal way to do it, I guess.
Right. So in one way it's a step up, and another way it's sort of a parallel step. And in the way up, it's that by having it in space, you eliminate a lot of the noise that's associated with detections on the ground. So what you basically got is two laser arms inside of a vacuum chamber, and for LIGO, that's the ground-based observatory, those are 4 kilometers long, and the sources of noise that they have to remove are everything from earthquakes to cows in a field, because these things are so sensitive. They're looking for changes in the length of the path of these lasers of smaller than the width of an atom. So in order to have that precision, you need to be able to remove all of these noise sources. That heating of the instrument itself can cause changes in the path length. So being able to have this...
Yeah, it seems like quite... like a huge obstacle of doing it here on the ground. And when I was reading about it, I'm like, at the end of the day, how can you be so sure that you're getting what you want to get? Because it's so difficult to get it all set up correctly.
Right. Well, one of the key things for LIGO is having those two detectors, one in Washington and one in Louisiana, because if you detect a signal in both of those, well, you can essentially eliminate a lot of the noise sources by saying, well, what's the chance that a cow walked over the observatory in Louisiana and Washington at the same time, or something like that. So
quantum entangled cows.
And then they're going to be adding a third is going to come online. A third ground-based observatory is going to be coming online shortly as well. So that'll add even more you get a sort of correlation between the signals from those 3 sites, and that really improves the likelihood of it's an actual detection. But with LISA, since it's space-based, not only do you eliminate the noise sources, you also have the opportunity to have a longer path length. So with LIGO, as I said, it was 4 kilometer laser beam arms, and the LISA ones are going to be 2.5 million kilometers. And what that allows you to do is look at a different domain of gravitational wave frequencies, just as there's different electromagnetic domains. You have ultraviolet light, visible light, infrared light. With gravitational waves, it's sort of a similar concept. So with LIGO, what you get is you're looking at the kilohertz range of, millihertz range of gravitational waves. So that's gravitational waves on the order of milliseconds. So the peaks and crests of waves are passing through the Earth at that frequency of milliseconds. And with LISA, what you're looking at is something more on the order of minutes. So that's in the kilohertz range. So it's a lower frequency, as I think the article said, that they're going to be looking at, and that allows you to detect different classes of objects, essentially. So in one way, you're improving the signal to noise, and in another way, you're also sort of opening the range of what you can actually see with the observatory.
So my understanding then is, with a lower frequency detector, the class of objects that are producing these gravitational waves are going to change, in the sense that, we're not limited to black hole mergers in our own galaxy anymore. We're going to be able to detect larger cataclysmic events in galaxy mergers that are happening.
Exactly.
many light years away, but because they're stronger events, but because they're so far away, that energy sort of dissipates a bit more over time to us. So we're going to detect, basically, in a sense, if this, if detections are picked up, well, we're going to know one way or the other whether or not this is a frequent event in the universe or an infrequent event in the universe. We see observationally galaxy mergers, but we don't know for certain if they're black holes at their cores merge into one object.
Right.
So this is going to be able to tell us more or less if that's a frequent event or an infrequent event, or if it doesn't detect anything, then maybe it never happens. So
right. And so LISA and LIGO are two of the three ways that you could directly detect gravitational waves, and the third is to use something called pulsar timing, and that gets you to an even lower frequency domain in the nanohertz range. And what those objects would be are actually primordial black holes that were formed in the first millisecond, or in the first second, after the Big Bang. And you might expect to see, and this is purely theoretical at this point, but you might expect to see an actual gravitational wave background like you see a cosmic microwave background, and that may be correlated with the fluctuations that you actually see in the cosmic microwave background might appear in the gravitational background.
Yeah.
So I'm not sure if I'm getting it exactly right, but there might be like some sort of background ripple throughout all of space-time that we might be able to detect that's sort of always there.
Right. So just like the CMB, where there's fluctuations, where we actually see the temperature fluctuations from the early universe, we may see basically density fluctuations that collapsed into black holes from the early universe. That's sort of permeating and radiating out these gravitational waves from these collapsing black holes from the Big Bang.
Yeah. And that's just a product of when you look out far enough into space in every direction, you're looking back in time to a degree. So, so that would be really interesting. The cosmic microwave background is, I'm going to get this wrong, is isotropic, right? Meaning that there's no preferred direction.
Correct, yeah.
And so necessarily you would expect a gravitational wave background to also be isotropic.
That's the idea.
But we'll see, because this will have sort of implications on maybe the Higgs field and what we can maybe learn more about how matter acquires mass over time. So this study, LISA, will really actually, or not LISA, the quasar method.
Oh, sorry. The other one is going to be the square kilometer array, and some of the other pulsar timing arrays, that's what the type of method is called, are going to be the ones that detect the stochastic gravitational wave background.
Gotcha.
So there's one being built in South Africa and Australia now that'll go online in the early 2020s. There's a Pathfinder mission in the Netherlands right now for that as well.
Interesting.
Yeah.
So I expect that experiment to really play more of a role in developing our theories of particle physics, more so than our theories of astrophysics, in a sense.
It could, yeah, and it could also have implications for cosmic strings and things like that. Again, purely theoretical at this point, but
cool.
I mean, it's a new way of a new way of seeing the universe, essentially. I'm very excited for it.
As are we. Very cool. Moving on. Number 2. Also on Tuesday, June 20th, NASA released its 529-page Ice Giants Pre-Decadal Survey Mission Study Report. You guys read the whole thing, right?
All of it. Yeah, is our quiz
500 pages.
The report details potential future missions to the planets Uranus and / Neptune, identifying the scientific priorities of such a mission over a range of budgetary options. Some of the reasons stated in the report's opening pages justify a future mission to the ice giant planets of our solar system more generally. For example, Both Uranus and Neptune have only ever been explored once by the same spacecraft. Voyager 2 flew past Uranus in 1986 and Neptune in 1989. And so that's the year Tom and I were born, and you weren't even born yet. So that's
and we just passed by.
And we waved. We just waved hello. And that's the extent of like our
knowledge.
Not our full knowledge, but like our
observational.
Our explorative nature of like really getting in there, nitty gritty, studying these objects.
And we've seen a lot of great stuff from Juno and Cassini that we've been talking about, and we've learned a lot of cool stuff already from those.
Correct. And think about how much technology has changed from 1989 to today. So
it's true.
These are good reasons to maybe go back. In addition, we now know, thanks to the Kepler Space Telescope's catalog of exoplanets, which we reported on trèSci last week, that the most abundant type of exoplanet in the Milky Way galaxy are those classified as mini Neptune ice giant planets. So terrestrial planets are abundant, but not as abundant as these mini Neptunes, right? So things that are smaller than a little smaller than Neptune, probably gaseous in nature, but not large enough, basically, to become extremely large gaseous planets like Jupiter or Saturn. So kind of this mid-range planet. So it would make sense for us to probably study these types of planets in depth in our own solar system, so we can get a better idea of exoplanets in our galaxy.
For when we send Matthew McConaughey there.
Exactly right. Exactly right. Finally, NASA expects to learn quite a bit more about how our solar system formed by studying the ice giants, since there exists a conundrum with how the planets fit in with our current understanding of the accepted model. Quote, for example, models suggest ice giants have a narrow time window for formation. Their rock/ice cores must become large enough to gravitationally trap hydrogen and helium gas, just as the solar nebula is being dissipated by the early sun. Forming earlier would cause them to trap large amounts of gas and become like Jupiter, and forming later would not allow them to trap the gas they have, perhaps 10% of their total mass. But if their formation requires such special timing, why are they so common? End quote. NASA's report goes on to identify 12 priority science objectives for ice giant exploration, 2 of which are deemed top priorities, while the remaining 10 are of equal importance to them, I guess. So I thought we could kind of go through those 12 science priorities, and I don't know, maybe it would be fun to commentate and sort of rank them amongst ourselves of what we feel
it's exciting to learn.
Should be included in a future mission to one of these ice giant planets. So I think we can all agree probably the top 2 that they deem top priorities, we would agree with our top priorities. So those 2 are to constrain the structure and characteristics of the planet's interior, including layering, locations of convective and stable regions, and internal dynamics. Right. So that's basically similar to what Cassini did for Saturn and what Juno is now doing for Jupiter. Taking a look below the opaque surface that we can see visibly with our eyes and instruments here, and sort of scratching below the surface and seeing what these planets are made up of, really, at a finer level, in a sense. So I think that we can agree that's pretty important to do.
Now, these aren't necessarily future mission goals. These are just what their priorities are, right? These aren't necessarily going to be incorporated in future missions. This is just what they think.
Correct.
Yeah.
Okay.
Correct.
It's like their initial report.
And the second one that they deemed a top priority is determine the planet's bulk composition, including abundances and isotopes of heavy elements, helium, and heavier noble gases. And I think we can both agree, or all 3 of us can agree, that that would be...
Yeah, you want to know what they're made of.
Yeah, that would be worthwhile. So the remaining 10, now, let's get into it. We can improve knowledge of the planetary dynamo.
I think this one's pretty important just because knowing about a planet's gravitational field, and that's essentially what the dynamo means, is how sort of the convection gives rise to the gravitational field the rotating core. And I think we can learn a lot about a planet just from understanding its gravitational field, sort of how, and the planet's environment as well, how its moons sort of behave in terms of where particles go, and what radiation is hitting where, and things like that. So I feel like that one's pretty important.
Yeah, I agree. I think it, not to sort of let the cat out of the bag, but you and I, Tyler, were both surprised when we saw the graphic that was put up along with this report, that both Uranus and Neptune currently are theorized to have some sort of liquid layer to them internally, whether it be of water or ammonia or a mixture of other compounds. I was not even really privy to that information, so that nobody has ever obviously directly studied that, but I guess from ground-based observations of these two planets, we must have some teams must have a pretty good idea that must be the case if they're kind of publishing graphics that are saying so.
Right. I actually thought that it was going to be more like, we'd expect it to be more like Jupiter and Saturn, and especially having a lower mass, expected to have like molecular hydrogen, down to maybe like a solid rock core or something. So I was kind of surprised to find that it's probably has some high density fluid or something.
Yeah. Same. Okay. So that's one there. We could also determine the planet's atmospheric heat balance.
I mean, I guess that's pretty important. I mean, we're kind of always wondering about our own planet's heat balance with how it's warming. We talk about that a lot on the show. And
that's true.
I recently read an article about saying that might be the best way to terraform Mars, is to be able to add our own sort of emissions out into the atmosphere to influence it, kind of. So I guess it's kind of important.
Yeah.
And I think that ties into both the previous point of the dynamo and how convection gives rise to sort of the mixing, and of course how heat moves throughout the atmosphere, and also how sort of winds behave and how heat actually flows across the planet's surface.
Right. Yeah. So I would throw that one in there too. All of these, I think, are going to be important enough. It's funny because I feel like each one of these little tickers here are basically layman's terms for a specific instrument that they have in mind that they need to put on.
It's going to be a very heavy spacecraft.
Yeah. So the other ones here, I guess we don't have to really scrutinize each one of them here. I'll just sort of read through the rest. Measure the planet's tropospheric 3D flow, zonal, meridional, vertical, including winds, waves, storms, and their life cycles, and deep convective activity. That one, I think, because there are so many people studying storms from Saturn and storms on Jupiter now, I think that's a gimme that people are obviously going to be interested in studying storm systems, particularly the storm system on Neptune that we know about already. Characterize the structures and temporal changes in the rings. Uranus and Neptune have rings, so yeah, it'd be nice to know a little bit more about them. Obtain a complete inventory of small moons, including embedded source bodies, dusty rings, and moons that can sculpt and shepherd dense rings. There's a lot to learn about how the ring dynamics work on these gas giant planets. Sort of a bonus feature of Cassini's mission to Saturn was learning that I believe it's Enceladus has ice volcanoes that erupt and eject material that feed into Saturn's
system.
I want to say F ring, but I'm not entirely certain about that. But yeah, so that creation of that ring is unlike the other rings that Saturn has, which is really interesting. Determine the surface composition of rings and moons, including organics, search for variations among moons, past and current modification, and evidence of long-term mass exchange / volatile transport. Map the shape and surface geology of major and minor satellites. Determine the density, mass distribution, and internal structure of major satellites and, where possible, small inner satellites and irregular satellites. Determine the composition, density, structure, source, spatial, and temporal variability and dynamics of Triton's atmosphere. Triton is a moon of Neptune, the largest moon of Neptune, one of the larger moons in our solar system, actually. And investigate solar wind, magnetosphere, ionosphere interactions and constrained plasma transport in the magnetosphere. So those are some of the mission objectives that they're toying with here.
For me, the take-home message of all of these is that there's so much about the planets in our own solar system that we still don't know about. So we've recently been talking about discovering exoplanets and what might be the signs of life and things on that, but just these planets in our own solar system and some of their really interesting moons that we really haven't even begun to scratch the surface on, that we could help us learn a lot more about life in our own solar system, perhaps even.
Absolutely.
So I'm excited to hear anything that we can learn from a mission like this.
Well, don't get too excited, because as this report was prepared for use in NASA's decadal survey, which includes a series of reports for future research exploration missions, we shouldn't expect to see a mission launched to either Uranus or Neptune until sometime in the 2030s.
I can wait.
Yeah.
I think it's worth waiting for.
So image credit goes to NASA JPL and Caltech and the Lunar and Planetary Institute for those images that we provided, which I don't know if Kyle provided any of the images there. Sorry, I didn't cue you on any of them. That's okay. I don't know if you guys...
You painted the picture.
I painted the picture. Did you guys see any of the other headlines from other science news outlets regarding future missions to Uranus and Neptune? Did either see any of this? So some of these headlines, you know, it's like we can't help ourselves with Uranus, right?
I know where this is going.
Some of them are like, NASA wants to probe Uranus for gas.
Just
that's the headline.
Bro.
Like
someone's just
seriously.
trying to...
Like, come on, guys.
They're like, how can we get so much on this?
Right? I get it. It's funny.
And then we got Alex Cohen in the chat says, my brother Tyler has no idea what he's talking about. I don't think that's true. I don't think that's true.
I specifically did not send him anything regarding this, actually.
We still found it.
Well, that's good news for us.
There you go.
Cool. Number 3. Remember last year's discovery of evidence for a 9th planet in our solar system? Something thought to be about the size of Neptune, orbiting the sun far beyond even Pluto's orbit?
I remember.
You guys remember this? Okay. Well, it turns out that there may not be strong evidence for a Planet 9 after all. The best evidence for Planet 9's existence had come from looking at 6 smaller Kuiper Belt objects that orbit the sun in highly elliptical orbits and exhibit clustering that was theorized to be due to the gravitational influence of another distant object about 10 times the mass of the Earth. And we have an image to show you guys what we're talking about with that. So the orbits of those 6 objects are highlighted here in different colors, and they're listed here. 2007 TG 422, 2013 RF 98. Those are kind of the designations of these smaller Kuiper Belt objects that, you know, the Kuiper Belt is kind of made up of a bunch of these smaller rocky, icy objects that orbit the sun, but orbit the sun in not such nice orbits, right? They kind of will swing in real close, and then
fly out really
fly
far
out really
away.
Exactly. Thank you very much. And then the dashed line here is the kind of proposed possible orbit of this massive Planet 9 that could be causing the perturbations of these orbits in the Kuiper Belt objects and causing them to cluster in such a way that we're apparently observing them. However, actually, to finish that thought, when multiple independent teams reported the same observations of clustering Kuiper Belt objects, the evidence for Planet 9 seemed strong. However, a team of astronomers leading the Outer Solar System Origin Survey, or OSOS, claim that observational bias may be the culprit of that apparent clustering. When looking at data collected over a 4-year period beginning in 2013 that carefully takes observational bias into account, the clustering of those highly elliptical orbits disappears. OSOS has had the capabilities to determine the orbits of over 830 trans-Neptunian Kuiper Belt objects, and when the team chose 8 of those objects to examine for more discrete evidence of the presence of a Planet 9, they conclude that, quote, the orbital distribution of the OSOS sample is consistent with being detected from a uniform underlying angular distribution, end quote. The team does acknowledge the fact that just because this line of evidence has fallen flat, it doesn't necessarily mean that there is no Planet 9 in our solar system, but we can expect disputes among the planet-seeking community until the ultimate proof of Planet 9 manifests, which would be direct imaging. Image credit goes to Caltech and our HERT IPAC for that image there. So I want to get your guys' takes on this because this was pretty big news when it hit kind of mainstream science news of this discovery, of evidence of a 9th planet, and now we are sort of getting fairly confident papers being written to refute it. So, Tyler, we'll start with you. What do you think about this?
So, well, first of all, we're seeing science happening in real time. A team publishes, Mike Brown and Konstantin Batygin, the 2 scientists from Caltech that published their study last year that theorized Planet 9. That was from computer simulations saying, well, if we see the clustering of these orbits of these trans-Neptunian objects, the only thing that we think could be causing those, this specific configuration of orbits is a 9th planet. And they did say that more observations are needed. Of course, there haven't been any direct detections, but now you've got another team of researchers looking back at another data set, a completely separate data set than the Caltech researchers were looking at, saying, well, you may have had some observational bias. But I'm not personally too worried for the fate of Planet 9. Well, of course, we don't even know if it exists yet, but I don't know if this paper is enough to really kill the theory. And actually, I was looking back at Mike Brown's Twitter account. Mike Brown was the scientist that theorized Planet 9. He's also the one that suggested we demote Pluto to a minor planet. And he had made reference to the paper on June 19th. He said, Planet 9 fans, okay, so I'm on vacation, but I haven't quite left for the airport yet, so take a quick take on the new OSOS paper. They demonstrated nicely that their survey is strongly biased, and I would 100% agree. They looked at limited places in the sky, and that makes biases. Now, Mike Brown, in his initial paper, it said this is where we should look for Planet 9.
And that's where they looked, right?
Well, that didn't cover the entire area. The OSOS survey didn't actually cover the entire area. These objects that were in this survey were discovered between 2013 and 2015. So these are not new objects.
Okay.
One of the things that they had said earlier, Mike Brown had said earlier, was I'm waiting for the next few discoveries of distant objects to see if they too have aligned and twisted orbits like the theory demands. Now, these aren't necessarily new objects. I think only OSOS has detected one new object, I think, last year, at least from an update from Mike Brown that I saw. So what he said was, I'd say the paper was relatively neutral for Planet 9, because they make the leap to say that therefore, because their survey is biased, no survey is good for understanding perihelion clustering. And that's not necessarily true, because these surveys back then were not designed with detecting a major planet beyond the orbit of Neptune in mind. They were made trying to understand, perihelion orbits of trans-Neptunian objects, but not necessarily to look for Planet 9. So I wouldn't say that this paper is enough to put the theory to rest. I think we need more observations from telescopes that are coming online in the next few years, like LSST.
Hype.
Yeah, we were talking about that before the show, and if you wouldn't mind explaining again what you mentioned about LSST.
Yeah, so that's the Large Synoptic Survey Telescope. Do you know when first light for that is?
2020, I think it's scheduled for.
So that is going to be able to detect a lot of new trans-Neptunian objects, and it has the capability. You mentioned you were talking with somebody at BNL who said it has the capability of being able to detect, directly detect
Correct.
the ninth planet.
Yep. It would be able to see at a magnitude of light coming from this proposed planet that it would be able to track it across the night sky, and we would be able to basically directly image it. And then once we find it, be able to kind of look more closely with better telescopes that can kind of zoom in on that particular object, right? So sky survey telescopes don't really have the capabilities of like looking up close and personal at an object. They kind of look over a wider area and can sort of track the really, really minute motions between objects that are bright in the night sky amongst themselves. But then other telescopes, like Hubble Space Telescope, for example, would be good at looking at this object by itself, in a sense. I mean, and Hubble Space Telescope actually wouldn't even be the best now, but it would be better than LSST.
Right.
So,
and just to clarify, that would be a direct detection. This clustering of orbits that they're talking about would be an indirect detection, because you're not actually observing the planet when you do this. You're just saying,
correct.
This we can explain. We can make a model that explains these parameters of clustering if we say there's a ninth planet in this position. And Mike Brown told us where to look, so I highly recommend following him on Twitter, actually, for updates on this, because he's constantly, giving rebuttals to new papers and stuff. He's at Pluto Killer. So,
Pluto Killer. That's a good Twitter handle.
But yeah, he's constantly posting updates on the search for Planet 9. And
So, you guys said something that sparked my interest in another way. Tom, I'll actually ask you this question directly. Getting people involved in this story, right? I think Tyler was the one that phrased it, that this is science as it happens, right? The evolution of science as it happens, which is absolutely true, right? Somebody makes a claim, and then other people it's their job really to try to do everything they can to, in a sense, dispute it, because we have to keep ourselves in check, right?
Right.
If we just go out and make a claim that there's a ninth planet
Because of this one reason,
right?
That's not the end of the story,
right.
Yeah.
That
a good theory is disprovable.
Exactly.
Essentially.
However, Tom, what is your feeling here with now the story trickling out through media outlets like ourselves and many others and into the mainstream public's eye? Is there any danger in that, in the sense of like, well...
Yeah, I can see what you're saying with that.
Because, and I don't want to like bring this up, but...
but we always have to.
But we always have to. We see this with the climate change argument of like, well, that got really released into the mainstream public's eye, and then it became a politicized topic, and now it's become a topic of contention where you can't even really talk about it openly without getting into an argument with somebody about it.
Yeah, so I'm kind of glad you brought that up. So a lot of times when I'm talking to people, they'll sometimes cite a new article that they found that might complicate like the idea of studying the climate. It might add another variable or another layer of depth to it. And sometimes in some people's eyes, when they look at that, they say, oh, they don't know for sure, they don't know what they're talking about. Look, there's already something new they just discovered 2 days ago. But that doesn't disprove what has been done, and like we were saying, it's science happening in real time. So a lot of people, I feel like, have a hard time understanding how people put out there their best idea, and then the scientists are taking that idea and going with it.
Mm-hmm.
Whereas a new piece of information doesn't undo what everybody else has done. It sort of all builds on top of each other. And a lot of times I see things being shared to shed doubt on other things just because it's a new piece of information. And they're saying, look, we didn't even know know this, and then they try and cast doubt on the whole thing.
Right.
Whereas people did a whole bunch of hard work building up to that point. You know what I'm saying?
Absolutely,
Right?
yeah. And I wish if there's one thing that I wish I could get across to people, it's not the actual studies themselves, but it's the process. If they could understand the process of science and what it actually means to be a theory, that it's sort of a collection of corroborating ideas and not just something some guy thought of one day.
Yeah.
And how that's built up and formed is probably more important than understanding,
Just
an
the
article on
message, yeah.
climate change or something. How those theories are put together, I think, is significantly more important. So absolutely, I totally agree with you.
Awesome. Now, of course, this topic wouldn't necessarily ever become a topic of contention.
Or be like, oh, there's no planet.
Pluto.
Yeah, exactly.
Well,
you never know.
Unless Bernie Sanders runs on the platform.
do I have time for my Pluto story? My
Yeah, go
Pluto
right ahead.
story?
Of course.
So, there's definitely, I would say there definitely is some drama in the planetary science community. Quick background, Pluto was, New Horizons, the probe to Pluto, was launched in January of 2006. And in August of 2006, the International Astronomical Union decided that Pluto should be demoted to a minor planet. And one of the loudest voices in the Demote Pluto choir was Mike Brown.
At Pluto Killer.
At Pluto Killer. That's why. Yeah. So, and Alan Stern is the principal investigator of the New Horizons mission. So just imagine having, your probe just launches, and then several months later, your probe just launches to go be the first to directly image the ninth planet, and now it's not a planet anymore. I mean, I'd be pretty miffed too, but yeah, so I was at a conference in January of 2016, and Alan Stern, the New Horizons PI, was giving a talk about the mission objectives and some of the initial images that they had gotten back and what they were expecting to find. And after the talk, I went up to him and I asked him for a picture. And in the picture, he put up 9 fingers. I said, oh, is that for 9 years? Because it took the probe 9 years to get to Pluto. He said, oh, it's for the 9th planet. So I begrudgingly put up my 9 fingers too, and we took the picture. I was like, it's not a planet. Not anymore.
So you're a Pluto killer too.
Yeah. You know what? I'll admit it. But, the idea of demoting Pluto had merit because it really didn't fit in with the rest of the planetary population. Now, I actually went about almost a year later, to another talk after Mike Brown had published this paper about theorizing Planet 9. I went to another talk by Alan Stern at a amateur astronomers conference, and in this one he was really sort of playing to the crowd, and this is after the papers had come out. He was like, I'm really upset with my colleagues at Caltech for diminishing Clyde Tombaugh's name. Now, Clyde Tombaugh was the one who discovered Pluto, and his children were in the audience. And so he was like, they dishonored, your father's name, and
get your pitchforks and your torches.
Yeah,
We're going.
The crowd was going crazy, and they were really eating it up. And I was just, there's no place for that. I mean, we don't.
That's not how it works,
right?
Yeah.
We don't say to Einstein, "How dare you, diminish Newton's name by, adding something or saying, his theory was incomplete or something like that." That's just how science works.
Right.
But, he was really feeding off the crowd, but there's definitely drama. It's a point of contention for scientists, maybe not for the general public,
Right.
but definitely when your theories and your probes are put into question.
Yeah.
You take it personally sometimes.
Yeah.
I would.
Absolutely. All right. Well, number 4, last story.
So I was gonna say,
Sorry.
if you think this is a good idea, if we could just give a brief summary of what number 4 kind of means, and then if we can see if we can get the stream
Yeah,
up.
definitely.
Absolutely. Yeah.
Definitely.
We are running a little late on time here. So number 4. This story is actually about a proposed 10th planet. So somewhere closer in to the sun.
So it would actually be closer than Planet 9?
Closer than where
This
Planet
proposed
9's
Planet
orbit
9
is proposed to be. But still further than the orbit of Pluto, so still way out there in the Kuiper Belt. A team of astronomers, Catherine Volk and Renu Malhotra, with the University of Arizona's Lunar and Planetary Laboratory, they report evidence of objects in the Kuiper Belt being, what we're going to say is 3 sigma off of the mean tilt of orbits that we...
So these guys are just more tilted than you would expect to see in that area.
Yep. So their proposition is that something massive
Something's got to be causing it.
has to be causing it, much like how we think we know about a planet 9. And this object would have the mass of something between the mass of Mars and the mass of Earth, perturbing these objects. So possibly terrestrial in nature would be this planet 10. And of course, much like with planet 9, we don't have any direct imaging evidence of this just yet. But this study is actually, I think, a little bit more well-founded in the sense of they're looking at all of the known Kuiper Belt object orbits that we have in this vicinity, in this distance range from the sun, and sort of comparing them to the other Kuiper Belt objects that we know of, and seeing some non-linearity in the nature of their tilts, basically. So seeing this like anomaly of the data means that there's something going on there. Whether or not we can say for sure if it's a planet or not is probably up in the air, but there's something happening there.
So would this be another case where we would learn a lot more with LSST and trying to absolutely
Yep.
We need the next generations of the next generation of telescopes to come online, and then I think we can really sort of put a lot of these things to bed, or at least the chances are good that we can do that.
Right on.
Cool.
So yeah, so that's.
And then we were joking about it a little bit, saying, now how do you tell which planet you're talking about?
Right.
We say planet 9, and then we say there's not a planet 9. Then do you say this proposed planet 10 becomes planet 9? Like, how do we? But then you don't want to call it a real name because it's not a real thing yet.
Yeah.
So
and the planet 10 orbits closer to the sun than the proposed planet 9. So really that one is planet 9, and planet 10 is possibly not even a thing, and nothing's really a thing. So it's it's a whole mess out there. It's a whole mess. Great. So let's
try and get some live pictures of the night sky.
Yeah, we're gonna let Tyler jump outside. He's gonna work on getting the telescope aligned and getting the camera online for us, so we can cut to that live feed of M81.
I'll tell you what, if it doesn't work out with M81, I will do like Jupiter or something, or
just
something.
Okay.
That'll be easy if I can.
Right on.
So I promise you something.
Sweet.
Hopefully.
So Tyler, thank you so much for you're gonna come.
I'll come back.
Okay.
Yeah.
Right.
You know what? I'll give you a ring if it's, or I'll text you or something. I'll put it in the chat so you know if I get it running, and then you can cut over to it.
Awesome.
Or if not, a frowny face or something.
Perfect. So we'll see you in a few moments when you come back. Awesome. Thank you.
Thank you for having me.
Yeah.
Thanks for being here.
All right. Well, I'll be back if it works out or if it doesn't. So.
Well, James said M81 already unsubs. So.
No. Dude, another funny joke was that you said Sigma 3 when you were mentioning the story, and our friend James has a video game alter ego at nighttime. He goes from geology during the day.
The evening fuzz.
The evening fuzz, yeah. And he is Sigma 3.
He is Sigma 3.
So you can't just say
I can't believe,
TM, copyrighted.
Yeah. Sorry about that, James. All right, so we have some downtime. So we were thinking about doing an impromptu Tom's Corner.
A quick Tom's Corner. So we're going to move from space and go down to Earth a little bit. This one I found really interesting, and I shared it with Chrissy while I was reading it, and it's about the Marshmallow Test. So have you ever heard of that before up to this point?
Very bare bones.
Okay,
so
if
you
we'll
want to
kind of go through it.
Yeah.
So the basics of the Marshmallow Test is you put a marshmallow in front of a kid, like a younger kid, and it's like 4, 5, 6 years old, and then you say, if you don't eat this, I'll let you pick from one of these two better things in like 10, 15 minutes. and then you see how the child reacts to seeing something he wants to eat right in front of him, and coming with that mental grapple of, all right, if I don't eat this cool treat right now, I'll get something better down the road.
Right.
So what this study was doing is they wanted to see how different cultures of children reacted differently. So this came from sciencenews.org, and it was, the title of the article is African Farmers' Kids Conquer the Marshmallow Test. So they tested kids in Cameroon, actually, and if you play FIFA, Cameroon has the fastest players all the time, so you should pick them. But besides that, Cameroon is, it's in Africa, so these children are brought up in a way that's different from most Western civilizations.
Absolutely.
So with some of the children in the study, the coolest part was they were so content with waiting. They were like, they understood, if I wait, I get something better. They sat there, didn't even get upset. A lot of the kids actually fell asleep because they were just not doing anything. They just sat there.
Fascinating.
And then some of the other kids from more of the European and Western civilizations, they got to the point where they didn't know how to sort of deal with their own emotions, and they got to the point where they would almost have a temper tantrum because they didn't really, not that they couldn't control their emotions, but it was just so frustrating to them. Like, why is this even being done? Like, why are you doing this to me? Almost?
Right. Well, that's what I would expect.
Yeah. So what the article tries to get into in the end is the type of parenting they think allowed these children to be better at being able to hold off from their impulses. So in the article they say it's, let me see, more authoritative parenting style. So that's not authoritarian like you're a dictator, but when you say something, it is what it is.
Mm-hmm.
Whereas, when you say something sometimes and then the kid puts up such a hissy fit, whereas you didn't want to give him french fries, but he bugs the crap out of you where, just give him a french fry.
Right.
And you do that a few too many times, and as they're growing, all they are is a little learner of information. And this, I really found this article interesting, how it could have implications to how they process information. So now, the last point I want to bring up to you is that they're trying to correlate this parenting style to the ability to reason out your wants and your desires. They're trying to correlate it down the road to being able to be a better learner down in the future.
Okay.
So I think it's kind of a stretch, but they looked at these people that were in the studies in the past, and they tried to follow up on them down the road. And I mean, it's not a direct correlation. You can't say this leads to that. But the study was trying to say that the children who had authoritative parents who sort of set a line, and when it is what it is, that they sort of were allowed to be, not allowed to be, but they allowed themselves to be streamlined into a more of an education type setting where they need to accomplish X, Y, and Z, and they went further in their education. So there wasn't that many kids, and you can't say that directly, and that's a big stretch to make.
Yeah.
But I think it's a really interesting thing to think about as a parent as you're going through. We have a buddy in this house who has a 3-year-old,
mm-hmm.
and my girlfriend's sister has a 1-year-old, and these are things I never really thought about until now. And my last question I want to lead up to you is, do you think that it's that important to have a certain style of parenting, or can you sort of just bring the logic in as they become 9 or 10? Can you just patch it up with the right logic as they get older? It's a very tough question.
That's a tough question, especially
we're no
parenting
experts. Yeah, I don't even have a kid, but I mean we're offering what we can.
Yeah. So I would look at it as definitely having a more authoritative style of parenting. It can't be something that comes later, right? Like, it has to be from the outset.
Yeah, I kind of had a similar feeling to that as well.
Because although in my own childhood, I feel like I can remember moments that are maybe epiphanies in the sense of like, oh man, I used to act like such a spoiled kid in this sense, and I shouldn't do that anymore. You know, like I sort of like remember moments of like maturity benchmarks in a sense. So you know, that nature I feel like is gonna fall on the individual child, right? Growing up to like come to terms with those sorts of things and say, all right, well, you know, I shouldn't worry about my desires so much that I have right now, because all in all, life's pretty good, and like down the road things can get better if I just listen to my parents, a little bit more and this and that. But as a parenting style, right, you can't really allow your child to develop that bratty nature and then want to course correct later on, because it's not going to work. You know, like it's going to be really difficult for you to kind of dig out of that hole in a sense. That's my 2 cents on that. Again, I'm no child expert. I'm no parent expert. So, but that's just how I feel about it.
So, I just wanted to go to the chat. Karen Riley in the chat said, could it also be that American and European children are addicted to sugar while those other kids are not? So, I actually didn't even really think of that. But I do think that's a huge part of our culture, where when you do something right or this and that, you get some sugar or a nice treat. Yeah. And that's sort of something that you learn to expect, I guess, as a kid. When I do something, I want this and I get that. And I guess that would play a part of some sort of bias in this experiment. Comparing two different cultures, it might already be ingrained for them to want the sugar that much more than their counterpart who doesn't really eat sugar every day. Right. You know, they just might like it that much more, but I think still overall that the parallels the test is trying to make still hold true.
So my 2 cents on that actually is the cultural aspect to this study might be more deep-rooted than just sugar, or like a want and need for sugar. I actually think it has more to do with the Western civilization's capitalistic, consumeristic nature of, you know, you see something you want and that instant gratification can be satisfied immediately.
And you get it.
You get it. And I think that that's something that isn't so readily available in places like Cameroon and places like Africa. And so children grow up without that thought even really permeating their minds.
When I want something, I can get it. It's not a direct...
It's just impossible sometimes for, you know, some of the things that they want and even need, in a sense, they don't have direct access to. So I think that is more of a cultural difference and something that we're seeing in terms of like that, I don't know, just that instant gratification. Like, I don't even know how to phrase it. Like, just being able to satisfy that instant gratification is so readily available here, and maybe not in other parts of the world.
Yeah. So, I don't know if we can make any profound conclusions from the Marshmallow study, but I just wanted to sum it up with when I worked at Brookhaven Country Day Camp, and I had a whole bunch of little 7-year-olds all day. The best way that I could sort of relay this like being in control of your own emotions was, I would sit them all down when they're all being jerks and not listening to anybody. And I would sit them all down like, we're not going to have fun unless we're all able to do the X, Y, and Z that we need to do to keep everybody safe. And then once we do that, then we can have fun. And I was like, so I'm telling you the directions, but I'm not the one telling you what to do. You are the one telling yourself what to do. So when you see that one kid lashing out, it's not that he's not listening to me. He's not able to listen to himself to be able to put himself in control of his own emotions and body to keep him in check so we can all move on, do what we need to do, and then have fun like we always do. Right. Where I try to get them to feel like it's not me telling you that makes you do it. It's that you hear the right thing that you need to do, and then you're the one that tells you how to do it. And you'd be surprised, kids who are like 6 and 7, how much they get that.
Yeah.
And they say, you know, sometimes I don't like listening when I'm hungry or when I do this, and they get it.
Yeah.
And I'm like, you know, you're the one who's in control. I mean, I'm going to sit you in the corner when you're not listening, but you're the one who's in charge of your own actions, and they get it from a very early age. So
Yeah.
I love reading and learning about this kind of stuff, though.
Yeah.
Really interesting.
Me as well. Nancy Cluta says, I'm about delayed gratification, improves character and teaches the satisfaction with the process. Happiness is not necessarily getting what you want, but the journey. And I think that's extremely well-founded. I agree with that as well. Andy says, yeah, it's more productive in character forming when the focus is on what you're doing to earn the reward or outcome rather than the reward itself. Journey, not the destination, or something like that.
Yeah, similar thoughts.
I agree. Yeah, and going back to what I said earlier, I think that those sort of manifest within the individual. I don't know that that's something you can really hammer into a child from a parental standpoint. Like,
Yeah.
I think you can do your best to get that point across, but I think that really has to come from within to understand that hard work pays off in the long run, and you have to see it. You have to do it. You have to do some hard work, and then see the you know, the fruits of your labor, in a sense, to really truly understand that.
Yeah, as my buddy Torbjorn says, hard work pays off. That's an Overwatch joke.
I love it.
Sorry.
I love it.
All right, so did we get any word from Tyler?
I haven't.
If we can get some live sky, because I would love to be able to show a nice image, because he has a really nice telescope out there.
I haven't gotten the promised text message. Kyle ran out there to help him, so I think we're closing in on confirmation, yay or nay.
Okay. With astronomy, when you're trying to live view something, as you know more than most, it's difficult to get it all set up to look at something in the sky.
Yeah.
And get it all to work out, but
Absolutely.
it would be great if we could see something.
Yeah. So I guess what else can we do to fill time here for just a few more moments?
So what is it that he's trying to set up out there?
Okay, that's a great avenue to go, Tom. Very good. So what he's got is a Celestron reflecting telescope. Basically what that does is it bounces light off a mirror, amplifies the magnitude of what you're looking at through an eyepiece. Getting there? Cool. Hooked up to that, he's got something called a Malin cam, which is a custom-made camera for detecting the very faint light that comes from deep space objects.
Oh, okay.
Right. So with your normal telescope, you can very easily attach an eyepiece, hook it up, point it at something like Jupiter, which is pretty easy to find in the night sky, and see it. Right. With something like a galaxy that is, you know, thousands of light years away from us, the light is so faint that the individual photons are not really distinguishable to our eye, because there are so many more relatively bright things for our eye to pick up on.
Okay.
And so what the camera allows you to do is it basically holds the shutter open and can pick up these photons that are falling incident on the sensor and collect them over time to then build
an image that we can then look at.
Exactly.
So James in the chat asked, what is M81? And then Andy said it's a galaxy, right?
That is correct.
So that was what he was initially trying to bring up, because M81 is something that is decently easy. I mean, as you could say easy in astronomy, but something, a cool galaxy that you can see in the night sky.
Yep. So M81, the M stands for Messier. Messier was a French astronomer who created this catalog of kind of brighter, more interesting objects that you could see through a telescope like this. And M81 is the 81th object on the catalog as he was going through the night sky. It's known as Bode's galaxy, and it's a spiral galaxy, much like the Milky Way galaxy is. It's in the constellation Ursa Major, which is
The Big Dipper.
The Big Dipper, right? So there's that. So we've got the telescope, we've got the Malincam. Hooked up to that is a cooling system because the camera is working really hard. The electronics of the camera are working really hard to keep the shutter open, collecting the light, transferring that information in real time to Tyler's laptop, and because of the sensitivity needed to basically detect faint amount of photons, you can't have heat then sort of dissipating into the sensor because that will obstruct your image. So he's got a cooling system that he was telling us can become really complicated because the moisture in the air will then
condense because of the cooling.
Correct. And freeze on the sensor of the camera. So I don't know if he has this set up tonight, but what he's had to do in the past is put the camera inside a plastic bag with a little silica gel
To absorb,
packet to absorb the moisture of the air, keep the air dry. It's a whole mess.
Just look
just
at a
to look,
galaxy.
yeah. So a lot's going into this right now. But you know what? I believe in Tyler.
I think he could.
If
there's anybody who could do it,
I think he's gonna do it. He's definitely not gonna let us down like the NASA Wallops launch.
We're still waiting on the NASA Wallops.
Yeah, we'd be really in trouble if we said we were gonna cut to another stream again and then it didn't work.
So we're not a go.
So we're not a go.
We are NASA Wallops.
We are NASA Wallops.
No.
Oh man. What is the final verdict over there, Kyle?
Just not really getting it all lined up, so really needed to align earlier. So
Gotcha.
Seeing he's that Martha, I'm just gonna shoot it in the dark.
All right. So do you think it may be possible to get the image and maybe we could like tweet it out or put it on Facebook, whatever we do end up getting, possibly?
Yeah.
Maybe next show.
Yeah.
Maybe next show we
Possibly.
can just show you what we got. Yeah.
If Tyler's feeling very determined out there and he wants to get it up and running, we can always come back online. But for now, Kyle, if you wouldn't mind just bringing Tyler back in, just so that we can sign off on the stream to wrap up this episode.
Yeah.
Right. That way, this episode can just exist
And on YouTube.
on YouTube for people to look back on.
Yeah, it was great having Tyler here, though.
He's awesome. Super, super cool guy.
Yeah, the first time I met him was actually at the astronomy.
At Astrofest?
Yeah, it was the first time I met him.
Really? Awesome.
You know, I was also thinking, which is kind of funny. I never officially joined the astronomy club, right?
No.
I kind of was just there.
Yeah, you
every
came
once in a while.
You came to a few meetings because we would just have classes late, and then I was like, "Oh, I gotta go do this thing. You wanna come?"
Yeah. I think I was having trouble with a few classes, and I was like, I can't really do anything else or else I'm going to fail.
Yeah, it's funny because astronomy club started more of like almost like an Alcoholics Anonymous, where like all the members at first were like, man, we are just so fed up with Stony Brook and we need to vent to each other.
Let's get together.
So let's get together and do that. And then Tyler and others really took the baton and ran with it.
And actually made it
a respectable club that I can now use on a resume, which is
like,
fantastic.
So Tyler's back. See if we can get him back in frame. There we
Sorry, I failed you. But
We are NASA Wallops.
We are NASA Wallops, man. No, it's okay. We were trying to explain to the best of our ability how complicated your setup is out there between the telescope, the Malincam, the laptop, alignment, cooling systems, the whole kit and caboodle out there. So our audience, they're cool, man. They appreciate the effort, and we wanted to just get you back here just to wrap up the show. We wanted to, of course, say thank you for being on the show with us this week. Like I said, this is a big step for us as trèSci continues to grow and build. Having guests on the show has long been a dream of ours, and we're really honored to have you kind of be the premier first guest on the show. So thank you again.
Thanks for having me.
Yeah.
Thanks for having me.
And hopefully in the future, as you do more research and come across things, when you want it to be publicized, we'd love to have you back on the show or anything like that.
Yeah,
Absolutely.
right on. So any closing comments from either of you guys?
No, I mean, with regards to the telescope, that's pretty standard for, nothing really ever goes completely 100% right. In tonight's case, it went 0% right. But that's just the way astronomy is.
That's how
sometimes
it goes.
your equipment works, sometimes it doesn't, sometimes everything's working perfectly, and it's cloudy.
Yeah.
And,
Yeah, it's just how it is. It's just the nature of the beast. Yeah.
But thanks for tuning in, guys.
Cool. Thank you guys so much. We will be back next week.